In this video, we're going to talk about the fundamental theorem of algebra, which we've been alluding to earlier, but we're going to formally write down here. I'm trying to be efficient, so I've already written these down. If you need to pause it for a moment so you can copy it into your notes or at any time, feel free to do that. So the fundamental theorem of algebra says if a polynomial p of x has degree n, then p of x has exactly n complex zeros. If we don't allow complex numbers but only real numbers, then we change this and say p of x will have at most n real zeros. So for example, the first one here, y equals x minus 2 cubed times x plus 3 squared. We have that the complex zeros are those things that make this equal to 0 that are complex numbers. And we can see that 2 and negative 3 do that. Those are real numbers, and all real numbers are also complex numbers. Now remember, the way we're counting this is we're going to say that 2 has multiplicity 3, and that negative 3 has multiplicity 2. And so that still, in our counting scheme, is going to count for 5 zeros because the degree of this polynomial is 5. So it has 5 complex zeros. We might think of them as being 2, 2, 2, negative 3, negative 3. And those are also, in this case, 5 real zeros. Now, the second one, if we set this equal to 0 to find those zeros, you can see that we end up taking the square root of negative 1, and so what we get is I and negative I. So this has two complex zeros, I and negative I. It has no real zeros because I and negative I are not real numbers, but remember we modified this to say it has at most n real zeros. So this is an example of a polynomial that has two complex zeros and no real zeros. So the linear factorization theorem says that if a polynomial p of x has degree n, then it has exactly n factors. So that's piggybacking on what we did with the fundamental theorem of algebra. Anything that is a 0, then x minus that will be a factor. So let's talk about, and let's try to also clarify this and this important difference between the real and the complex numbers. So if we start with a polynomial p of x equals x to the fourth minus 1, and we want to find the real zeros and factor it over the real numbers, and then the zeros and complex numbers, we'll factor it there. So we'll start by factoring this as the difference of two squares. And so we can see that the x squared minus 1 will factor again as the difference of two squares, but that the x squared plus 1 does not factor over the real numbers. So as we saw in the example earlier that we put up here, the zeros for x squared plus 1 are going to be imaginary. So our real zeros for this polynomial are going to be only 1 and negative 1. I and negative I are zeros, but those are not real numbers. The factors then over the real numbers, if we're only going to allow real numbers, our factors are exactly what we have here, x minus 1, x plus 1, x squared plus 1. So if we're going to allow only real numbers, we cannot guarantee that we're always going to get to what we call linear factors, x plus something or x minus something. We may have to settle for a quadratic factor, a prime or irreducible quadratic. Now, if we're going to allow complex numbers, then we saw before that our zeros are going to include I and negative I. So we'll get 1, negative 1, I, and negative I. Those are the zeros, and the factors over the complex numbers are that p of x will be x minus 1, x plus 1, then x minus I, and x plus I. So just trying to clarify the difference between complex and imaginaries. Hope that makes sense. Let's do some more examples. So let's find the zeros and factor We're going to find the zeros and factor. And here we're going to assume that, unless it's otherwise stated, that we're going to be working with the complex numbers. So we'll say p of x is equal to x to the fifth minus 4x to the fourth plus 4x to the third. So to find zeros, we're going to set equal to 0. We're going to factor that so we see a greatest common factor of x cubed, and that's going to leave behind x squared minus 4x plus 4. And that factors further into x minus 2 times x minus 2, or if we like, we can call it x minus 2 squared. So our zeros, now we know that there has to be 5 of them because it's a fifth degree polynomial, but we can see from our factorization that some of these are repeated zeros, repeated roots. They have multiplicity greater than 1. So we get 0 and 2 are the only distinct zeros, the only ones that are different from each other. We know that 0 is going to have multiplicity 3, and that 2 is going to have multiplicity 2. The factorization then is going to be just what we did there. P of x is going to be the x cubed times x minus 2 squared. Let's try another one. Let's say this time y is equal to x to the third plus 4x. So again, we're looking for zeros and factors. We can factor this time an x out of that, leaving an x squared plus 4. So if we want to solve this perhaps first, we know we're going to get x equals 0 from that first factor. If we take x squared plus 4 equal to 0 and subtract the 4, and then take the positive and negative square root of negative 4, we're going to get a positive and negative 2i. So our zeros for this third degree polynomial are going to, there should be 3 of them, and there are 0, 2i, and negative 2i. The factorization for these is that y is going to equal x, what did I suggest, x times x minus 2i times x plus 2i. Okay, let's do one more example of this where we're going for zeros and factors. So I'm going to say f of x is equal to x to the fifth plus x to the third plus 2x squared minus 12x plus 8. Now, this one, we don't know how to factor this. We don't have a good strategy. So we're going to use our rational root theorem to try to find some zeros that will get the ball rolling here. So we need to, since this is a fifth degree, we're going to have to come up with 3 zeros using the rational root theorem so that we can eventually use synthetic division to get it down to a quadratic. So remember, the p's are the things that are going to divide into the constant evenly. So that could be plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. The q's are going to divide into the leading coefficient evenly, and fortunately enough, that means we're going to have just plus or minus 1. So our p over q's are going to be the same list that was our p's. They're going to be 1, 2, 4, and 8. So let's see if we can make this work. We're going to put 1 up in the box. We're going to write our coefficient. I'm going to try 1 first. I'm going to go 1. We have 0x to the fourth, 1x to the third, 2x squared, negative 12x, and an 8. And we're hoping that we can get a 0 in this position here. If we do, then we have one of our zeros. Remember, we're going to have to do this and repeat this until we can get 3 zeros that work to break this down from a fifth degree down to a quadratic. So using synthetic division, I'm going to go 1, 1, 1, 1, 2, 2, 4, 4, -8, -8, 0. Bingo. We got one of them. Now here's where you have to be careful, especially with something like x to the fifth. I wouldn't go on to the next one yet, but I would try, building off what we just did there, I would try that same 0 a second time. Because remember, it might have multiplicity 2 or 3 or something greater, and so it might be a 0 again. And so if I do that, we're going to go 1, 1, 2, 2, 4, 4, 8, 8, and sure enough, it is a 0 again. Well, how far can we push this? Let's try it another time and see if we can get down to our quadratic. 1, 1, 3, 3, 7, 7, 15. Nope, it didn't work. So that's too bad, but we can try something else. So I'm going to go back to, let's see, I'm going to try, now I'm going to change color here, and let's try, and because I actually know what is going to work, I'm going to jump to that. I'm going to pick up these coefficients where we left off, 1, 2, 4, 8, and see if we can get this to work. So doing synthetic division, we have 1, -2, 0, 0, 4, -8, and there is a third 0 there. And now the good news is what remains is a quadratic. So from here, we're getting x squared plus 4 is equal to 0. Well, we can recognize that doesn't factor over the real numbers, but if we solve it and we take all possible square roots of -4, we're going to get 2i and -2i. So we can now answer our question. The zeros of this fifth degree polynomial are 1 with multiplicity 2, so it's going to count as 2 of them, and -2 and 2i and -2i. So there's the zeros, and the complete factorization is going to be f of x equals x minus 1 squared, because 1 was a 0 of multiplicity 2, x plus 2, x minus 2i, and x plus 2i. Very good. Okay, I'm going to stop here and make a second video on the fundamental theorem of algebra next.